you're given a DSP chip shown in red, and you're also given this digital filter that has the transfer function h of z that has a third order polynomial in numerator and seemingly a third order polynomial in denominator. The question is, can you realize this h of z digital filter using just minimum numbers of this chip shown in red? And if so, how do you use them? How do you connect them together to realize the transfer function h of z shown here? Okay, so let's first understand what this DSP chip shown in red is doing. So input samples like x of n comes in, and you can see the flow of sample is downward through the 3 registers. And then after at the output of the register 1, you have xn minus 1, which means 1 sample delayed. And then xn minus 2 at the output of the second register, which means 2 samples ago. And xn minus 3 at the output of the third register, which means 3 samples ago, is preserved there. And every clock, these registers are working like a shift register, so pushing data toward inside each other. And then what happens is we have a multiplier C0. These C0, C1, C2, C3 are the value of 4 multipliers inside the chip that we can program. So what comes out, which means output sample yn at any moment, let's say at sample moment or sample number n, is C0 times x of n. As you can see, x of n is multiplied by C0 plus C1 times x of n minus 1, so C1 times x of n minus 1, plus C2 times x of n minus 2, plus C3 times x of n minus 3. So that's the most this filter can do, this chip. So it can at most realize a third order sort of feed-forward non-recursive. So we say it's a non-recursive design or implementation. So just be careful about that. By non-recursive, meaning it's feed-forward. So as you can see, input samples are coming in. They flow through the registers and multipliers, and then they sum up and generate an output. There is no feedback loop, meaning that from output, we are not going back into the system. So that's why we are saying it's a non-recursive, basically FIR implementation. But as you can see that the h of z is given here is not FIR, because FIR filter does not have a denominator that has order beyond order 0. So here we have an IIR filter, IIR digital filter. So how are we going to use this chip to realize it? Well, think about it this way. Effectively, this filter is a numerator in the form of a third order polynomial. So that's nz, that's a numerator polynomial in z, and a denominator polynomial in z. Fine. Okay. So let's for now, the numerator polynomial, one thing you can see is if you factor out 24 out of it, just to make it nicer, 168, 24 factored out is 7. And then let's also factor z cube. So 24z cube factored out, and then you end up with 7 plus 3, because 72 divided by 24 is 3, and then z to the power 3 is factored out, so it becomes 3z minus 1 plus 36z. You factor out 24z cube, so you end up with 1.5, and then you end up with z minus 2. And finally, you have 24 that you're factoring out 24z cubed from. So therefore, you end up with z minus 3. Nice. So that's the situation for the numerator. But what about denominator? Okay, so let's multiply. If you do so, I'm going to use a different color so that it is clear what I am doing here. So I'm going to use this color. Okay. So if you multiply, what is the thing you're going to get here? You are going to get 24 z, because 8z, 3z squared become 24z cubed, plus then you have 19z squared, and then plus you will end up with 10 z, because it is 8z times 1, and then 1 times 2z, so 10z, and then plus 1 finally. So that's your denominator. So let's also factor out 24 out of this denominator, 24z cubed. So if I do so, this denominator will become 24z cubed times, it will be 1 plus 19 over 24z minus 1 plus 10 over 24, that will be 5 over 12 z minus 2, and finally 1 over 24 z minus 3. And then that's it. This is my polynomial. So what I can do is I can substitute this, and you can see that both numerator polynomial is factored out 24z cubed, and denominator polynomial is also factored out 24z cubed. So those cancel out each other, and therefore my h of z effectively, let me use a different color. So my h of z effectively becomes this. So nicely in numerator I have just 7 plus 3z minus 1 plus 1.5 z minus 2 plus z minus 3. And in denominator I just have 1 plus 19 over 24 z 19 over 24 z minus 1 plus 5 over 12 z minus 2, and then 1 over 24 z minus 3. Okay, so what is the benefit of this? Z minus 1 in digital design correspond to delay. So what you saw here that I wrote in terms of the input-output relationship for the output sample as a function of input sample entering this chip, if you do the z transform of it, it is effectively y of z equal to c0 x of z, I'm going to factor out x of z, c1 z minus 1 x of z plus c2 z minus 2 x of z plus c3 z minus 3 x of z. So that's it, and this is x of z factored out. So what I'm trying to say is relationship between x of z, or the transfer function of input sample, and y of z, transfer function of output sample, as realized by this filter in red in this DSP chip, is this FIR, or non-recursive transfer function g of z. And as you can see, we can, and C0, C1, C2, C3 are programmable multipliers, so we can program whatever we want. But as you can see, as I said earlier, this filter can only realize a third order FIR. So very nice. We are also in need of third order implementation for the polynomial in numerator and polynomial in denominator. But the thing is, polynomial in numerator is only FIR1, not in the denominator. So what is the thing we are supposed to do then? Okay, so the thing we can do is now this step. So my h of z, as I summarize here, so h of z ended up to be what I wrote there. So it's 7 plus 3z minus 1 plus 1.5 z minus 2 plus z minus 3. And denominator, we just summarized. I'm just writing one last time so that I can manipulate this to the point that I can show that I can use the chips provided and realize this whole thing. Okay, now let's play this game. This h of z is effectively y of z over x of z for the overall system. So in this case, you can say that this whole thing in denominator multiplied by y of z equal to this whole thing in numerator multiplied by x of z. So I can just say y of z, that is the impact of this one. So let me change the color so that it is clear what I'm talking about. So this 1 multiplied y of z, I'm going to write it as y of z. And then the rest of it multiplied y of z, I'm going to push it to the other side. So it will be negative 19 over 24 z minus 1 plus, I can just keep it plus for now, but I'm gonna distribute this negative inside. and 1 over 24z minus 3 times y of z. So I didn't do anything weird. I just multiplied this portion by y of z and moved it to the other side of the equation. Plus, let's name this whole thing as nz, which is a third order straightforward polynomial in numerator. So I would just write down nz x of z. Great. Okay. So we are almost there. Last step to just clean it up. I'm gonna do this last step. It's already clear what I'm doing. I am going to actually I can do it right now. So how about we distribute this minus sign inside this parentheses, so it become minus, and it become minus, and it become minus. Okay, so what is the benefit of this? Well, we are almost done. This is the overall output of the system for the given transfer function we want to realize. We are saying it's equal to output multiplied by a third order polynomial, straightforward, plus input multiplied by a third order polynomial. So, and we know the chip can implement a third order polynomial. So what's going to happen is, first I need to grab the input of the system. Okay, great. So input samples. Let me make sure that you guys can see this. So, okay. So what's happening is, I'm going to use a different color so that it is clear. Okay. Input samples. X of n. Xn. So that's input samples at index n, or moment, sample moment n. They enter a chip that is supposed to realize nz. Okay, so it's supposed to realize n of z, which is the third order polynomial in numerator. But what is n of z? Take a look at it. It is effectively 7 for C0, 3 for C1, 1.5 for C2, and 1 for C3. So very nice. Effectively what I'm going to say is I'm going to use one such chip given here, in which C0 is 7, C1 is 3, C2 is 1.5, and C3 is, okay, and C3 is 1 over 24. That's one chip. And what is going to come out of this one chip that I used for this purpose? It will be the intermediate output. So just wanted to make sure we are on the same page about what I'm realizing. I just realized this portion. So I just realized this portion of the summation. This portion. Okay, so what is the next step? In the next step, I need to also, now let me use a different color. So I need to realize this portion now. I need to realize this portion. Okay, fine. So how can I do that? Let me just remove these guys that I just, now it's better. Okay, so to do so, looks like I need an adder that adds the result of what I just did with the outcome of another chip that is basically taking, okay, so let me make sure that we have enough space to show this. Okay, so I'm taking the output, which is y of n, with, when I said y of n, it's n domain or time domain. Of course, correspondingly in z domain is y of z. Same thing about x of n. In n domain or time domain is x of n, its z domain is x of z. So we are feeding back y of n to the second chip that is realizing this whole thing. And you can see that to map this whole thing to what chip can do, C0 has to be 0 because we are not having such coefficient here. But then C1, which is the coefficient for Z minus 1, as you can see, C1 is negative 19 over 24. So I'm going to write it here. C0 has to be 0. C1 has to be negative 19 over 24. And C2 has to be, as you can see, C2 is a coefficient of Z minus 2, so it has to be negative 5 over 12. Negative 5 over 12. And C3, the coefficient of Z minus 1, Z minus 3 has to be negative 1 over 24. So that is the second chip I'm going to use, and the output of the chip as coming out is basically the result of, so the output of the chip that is coming out is what I need to just sum, as shown with this adder. So I am doing this addition. That is the representation of this add. And this will become the output of this add is effectively the output that I want. So let me just shift this whole thing so that it is clear. There you go. Okay, so this output that I got is the final output that I need. It goes out. Therefore, the scheme is input samples are coming in, entering the first chip with these C0, C1, C2, C3 coefficients that I am showing. Then we need to use an external adder that is interfacing between the two chips because the second chip is shown here. It takes the final output samples as input, generate intermediate results, add the intermediate results to the output of the first chip, and then the output of this adder will generate the final output that we desire. So this is an interesting example showing that using just the implementation ready for us that is a non-recursive or FIR implementation, how we can realize an IIR or recursive implementation using two such chips as is shown here. I hope that this example is useful.